Good afternoon and welcome. Thank you for joining our session, From Design to Device, Showcasing EVE Capabilities. This is the second webinar in our EVE series following Designing Seamless Interfaces, Moving Beyond MCU Limitations, now available on our YouTube channel. If you missed it, I recommend watching for a deeper look at our EVE products. I am Bonica, host for this webinar. Together with me, we have Gavin Moore, your moderator in the Customer Engineering Support team. Gavin is here to ensure our session runs smoothly and will be managing your questions throughout the webinar. Hosting with me are Graham Brown, our CES team leader, with over 15 years guiding customers and distributors through complex projects. And Aaron Jones, our CES engineer with over a decade of experience designing intuitive user interfaces. A bit of housekeeping. We'll have a Q&A at the end. Please submit questions in the chat anytime. If we run out of time, we'll follow up by email. You can also reach us at support.emea@brtchip.com. This session is being recorded for later viewing. Let's get started. I'll hand over to Graham to kick off today's discussion.
Thank you, Veronica. Hi, everyone. In today's webinar, we'll tell you a bit about Bridgetek. We'll give you an introduction to EVE as a recap of the previous webinar, and Aaron will present that. And we'll give you an overview of our Bridgetek EVE toolchains, followed by a demo session where we'll demonstrate 6 ways to develop your user interface with EVE, including a brief overview of the hardware, the Bridgetek toolchains, libraries and examples, a way to use LVGL with EVE, and how AI can help you develop with EVE. And overall, we'll show you how you can take your project from concept to simulation through to physical product. And we'll finish up with a Q&A session.
Bridgetek, a global semiconductor company, specializes in innovative bridging solutions, including HMI solutions and microcontrollers. We are well known for our embedded video engine graphic controller, ICs and modules, which integrate display, audio, and touch functionality into a single chip. This approach significantly reduces development time and costs for next-generation HMIs. We focus on innovative silicon solutions that enhance seamless interaction with modern technologies. Our key objective is to support engineers with feature-rich, robust, and easy-to-use product platforms. These platforms enable the creation of high-performance electronic designs with low peripheral component requirements and minimal power consumption. Our services do not restrict us only to providing IC components. We also offer customized hardware solutions, designing modules with displays and software as required. Partner with Bridgetek for your future visually impressive applications. Let's build the future together.
Thank you, Graham. So here's just a quick recap of Webinar 1, which has been recorded and is available via the QR code on the right-hand side of the page. We covered MCU constraints in UI design, how our EVE series of chips help to bridge this gap, and the benefits of hardware-assisted graphics. So just to go back, what is EVE? EVE is our embedded video engine, and this is a object-oriented graphics accelerator IC, which you can issue commands over I2C, SPI, or Quad SPI, depending on the version of EVE that you're using. These commands then will generate and render a screen via the video output on the Bridgetek EVE IC. The EVE IC also incorporates a PWM control for the LCD backlight drivers, as well as a touch interface, which can support, depending on the EVE model, capacitive or resistive touch engines. It also includes a audio output, which you can connect to an amplifier and speaker and play back audio sounds via inbuilt or custom audio files with EVE. So today I'm going to cover some EVE toolchains. These are a suite of free software tools and examples. And their main focus is to help you design, simulate, and deploy graphical user interfaces with EVE. So let's have a quick overview of the EVE toolchains available. First, we have EVE Screen Designer. This is a full what you see is what you get editor, which allows you to generate custom application pages and the logic between these pages. And it will generate the full source code for your application, including touch and images. The next is EVE Screen Editor. This is a static screen emulation tool, which you can use with lower level code projects, and is primarily targeted for people that want to learn how the EVE command instruction set works, and you can demo screens via USB to SPI connections on real hardware. We have our EVE Asset Builder tool. This allows us to convert any graphics assets that we require in our application, such as images or fonts, into EVE readable formats. And then finally, we have our EVE libraries. These are a set of software libraries that help you develop with EVE. We have two main ones. We have our EVE Apps, which is a Microsoft Visual Studio based library. And we have our EVE MCU Dev library, which is targeted to be a lightweight portable library for a variety of microcontrollers.
Thank you, Aaron. So when you're developing for EVE, this is just an outline of how you can do it. First of all, you can create your GUI layout using the EVE Screen Designer, EVE Screen Editor, or our code-based projects. You can then use the EVE Asset Builder to prepare fonts, images, and other assets. You can test the interface in the toolchain before you deploy it. And finally, you can output the compiled design to the EVE hardware and then incorporate into your MCU application. In the main part of today's webinar, we're going to be demonstrating the 6 different approaches to the development for EVE. So just to give you a brief overview of the hardware that we're going to be using today. First of all, we have our ME817EV, which is our Bridgetek evaluation board for the BT817, with an onboard USB to SPI and Quad SPI. For the display, we are connecting a Bridgetek DP0701-01A, which is a 7-inch 800 by 480 TFT with capacitive multi-touch. And we're using our VA1001-01A universal adapter to connect the display, RGB, and touch and interface between the two boards. But when we come to host the device, we are going to be using the onboard USB to SPI connection as shown here. And we'll then show you how to deploy your application to a microcontroller using the Bridgetek MM2040 EV, which is an onboard RP2040. On the software side, most of the demonstrations today will be using a color picker as an example. So we have the color wheel on the screen as an image, and the user can select the color by touch, and we indicate the selected color via a rectangle. Some of the demos have additional features, such as a slider for saturation level. But first of all, I'm going to hand you over to Aaron, and he's going to cover the first of our 6 approaches, which is ESD.
Thanks, Graham. So we are going to use our EVE Screen Designer toolchain here to create a color picker application. We're going to create the logic and program the logic flow. We're then going to simulate and deploy this to the RP2040 MCU on our MM2040 EV development module. So if we launch EVE Screen Designer, we're presented with the welcome window, and we can select Create to create project. Then we need to define which targets our project's for. As we're using the ME817 and DP0701-01A screen, we're going to generate a new target for this. So let's name our target. And then we want to select the EVE platform applicable. So the ME817 will give us BT817, LVGL for the screen resolution. The host platform, we're going to select FT4222, which is a USB to SPI interface, and then the applicable flash and touch options. So then we can deselect the targets that are not required in our application. And then ensure that the ME817 target we've generated is selected. We can then browse to select a folder where we want to save a project and give it a name, such as Color Picker ESD. If we select Next, this will give us our configuration page, which allows us to select how many pages we want in our application, if we need any custom source or widget files. And then we can select Configure, as we only need 1 page for this application. This generates a base project for us, and you can see our EVE Screen Designer windows here. On the left-hand page, where the pages are, this is our emulated screen layout pages, and on the right-hand main pane, is the logic flow. We don't need the user page here, so we can close that. We're going to generate our application in the first page that you can see here. As you can see, it already includes a label, and this is one of the inbuilt ESD widgets. So we might want to change the text on this label. For example, we can put Color Picker, and then we can click and drag this around the screen as required. So let's put it here. So the main component of our color picker is going to be a color wheel image, which we can add into our project by selecting File and Add, and then navigating to where our input image is. We've got a PNG here. And if we open this, this brings up the image converter utility. And there's a wide variety of settings we can use here based on color and size for our image, but we're going to select ARGB 1555 and convert the image. This then appears in the resources folder here, where the property window gives us some details about the image, such as its stored location and its size. So, ESD has a number of inbuilt widgets, and these can be found in the library pane here on the right-hand side. And conveniently, there is a color picker widget. Now, this is quite a complex widget that is supported in the Screen Designer toolchain, and we can click and drag this and position it onto the screen. We can use the properties window to set this to the size of our input image, so 250 by 250, and then we can use this bitmap drop-down to select the image we want to use. As you can see, it's emulated on the screen here on the left-hand side. So we might want some more widgets in our application. For example, we could add in a slider, which can be used to control the alpha output from the color picker, i.e. its transparency. So we can position and resize this as required. And then in the properties pane for this widget, we can set the max value to 255, which is the max applicable 255 alpha value, and set the starting value to 255. For example, we can also change things like the theme of the widget, and we'll give it a nice blue color here. Okay, so we need an output for our color picker, and we can use something simple like a rectangle, and there's a rectangular widget in ESD. Again, we can click and drag and position this on the screen as required. So if we're happy with our layout for our application page here, we can then perform the logic component of the page. So you can see in the right-hand pane, we have our logic nodes. We have a rectangular widget, our slider widget, and our color picker widget, along with the label that's also on the screen, and a fixed position node. So perhaps we could take the value of the slider widget and feed this into the lightness value of the color picker. And then we can take the color output of the color picker widget and feed this into the color input of the rectangular widget. So we might want to test this logic flow, and we can do this by saving the page and then running the simulation. And then we can use our mouse to act as touch input, and you can see that the output of the color picker is represented in the rectangle here, and the slider widget acts accordingly by reducing the alpha of the output rectangular box. So if we're happy with our application, we might want to test this on our hardware, and we can do this with our USB to SPI interface provided by the FT4222. So we can build and upload the code to hardware via this button here. And if we select this, this will build the application project and produce an executable file which will run the USB to SPI interface. And you can see this running on the hardware here, where the code is being running on our host PC over the USB to SPI interface and driving the EVE screen. You can see the exe generated here. So if we're happy with our testing on our real screen, one of the things we can do also with ESD is to check the resultant display list commands. These are the lower level EVE commands used to generate the screen. And if we're happy with all of this, we might want to port the project onto our MCU. So one of the things we might want to do is rearrange where the files are on our MCU. So if we select our color picker image, we can move this from a file to program memory, and this will recompile the project. And then if we select the MM2040 EV as our host platform, this will compile the C code required to run the project on the MM2040 EV. We can follow the same steps then by using the build and upload hardware button. We press boot select on the Raspberry Pi Pico. This brings up the memory device associated to the RP2040. And then we press the build and upload hardware button. And this will generate a UF2 file which can be used to program the Raspberry Pi Pico on the MM2040 EV. The toolchain will copy this on automatically for you, or you can drag it on yourself. And here you can see that the application code is now running on our MM2040 EV development module. Okay, so that covered ESD. Let's move on to ESE. Now ESE is a static screen emulation tool, And we can use our USB to SPI interface to demonstrate the screens we create on our hardware as well. And this is predominantly targeted for people that want to get into the lower level parts of their code and code manually. So as with ESD, there's a project creation page, and we can give this a name such as Color Picker ESE. Now, ESE doesn't have the complex widgets that ESD does, but it does include the base widgets that are available for use in EVE projects and are supported by the commands in EVE devices, as well as the primitives and other graphics controls. So for example, we can copy a text command on here, drag it across onto the screen, and this will give us the command text output in our coprocessor list, which are the list of commands used to generate the screen. We can manually edit this, or we can edit it via the properties window. For example, we can change the text to color picker, and we might want to select a different font. These handles are the inbuilt fonts, but you can use handles for custom fonts if you have generated these for your project. Again, the next step is we need to add in an image to use as our color picker. So if we'll navigate back to this image, and the bitmap conversion utility appears, we'll select again ARGB 1555 and hit convert. In the content window here, you can see that the image has appeared. And in the properties window, you can see that it's loaded at graphics memory RAM-G address 0, and it is currently loaded, but we can select to unload or change the address if required. If we click and drag this onto the screen, it produces the code required to render the bitmap on the screen. You can see this here, including a set bitmap and a vertex command. Again, we can manually edit this, or edit these commands via the properties window and move things around on the screen. Okay, so we want an output rectangular box, as we had in our previous application on ESD. So we're going to draw one of the rectangle primitives here. You can see there's a begin rectangles command and a vertex command. Let's copy this to create another vertex for our rectangle. And then we can click and drag this around on the screen as required. So if we're happy with the static screen we have created, we might want to test this on our hardware, and we can do this via USB to SPI. But first, let's check again, as with ESD, we can see the lower level commands used to generate the screen. And ESE gladly provides us with a live emulation of the internal chip registers as well, which can be helpful during debugging. So we have our commands to generate our screen here. We want to test them on hardware, so we can use our 4222 on the ME817EV again. So let's check that we have our project settings correct. We've got it set for a BT817, and we have the resolution set to WVGA. So there's a multitude of WVGA screens, and we might want to change the settings for these. And you can see that the devices currently only list the emulator, which you can run on ESE. But let's refresh, and you can see that the 4222 has appeared. So let's manage the devices we have. So we've configured a specific device for our DP070101A screen, and this has all the applicable register timing settings for the screen here. So when we connect to the device over the 4222, we want to make sure we're using the settings correct for our screen. So we select this in the devices here, and then we can press connect. This will boot up and connect to the screen and give us a blank screen at start. And then we can use the write RAM-G and RAM command button here to write the command list to the screen and display our screen. So we might want to move some things around. For example, the output rectangle, maybe that's needing resized or positioned somewhere else. And we can do that with the drag and drop nature of this toolchain, and then hit write RAM command and RAM-G update again. And this will reposition it on the screen for us. So this allows us to view what our screens would look like on a real hardware. But what if we want to export this to an MCU? Well, we can via the export tab. We've chosen an EVE MCU Dev lower level library project here for the Raspberry Pi Pico. This generates a full Raspberry Pi Pico project, which we can import into Visual Studio Code using the Raspberry Pi Pico extension. So let's click on the extension here and go to the import project function and navigate to where this imported project, or this project has been generated. We select import, and this will import the project into Visual Studio Code for us. You can see that the project has a number of files, including the EVE MCU dev library files and a common folder which has the project files in it. For our example, if we navigate to eveexample.c, we can see some library-specific commands here that mirror the commands that we have generated in EVE Screen Editor. So, there's a couple of things we need to do before we build this project, one of which is check the cmake.list file to ensure that the following standard USB is enabled, standard I/O USB. This is to power the development module, and then we want to take the eveconfig.h data from the file in the top level folder and copy this into the eveconfig.h file in the library structure. This is the settings used in ESE to demo our project on the screen, and we want to make sure when we build the project that the same settings are used and pulled into the library. So once this has been done, we can use the extension again to hit compile project, and just like ESD, this will compile a .uf2 file which can be used to program the RP2040 on our MM2040 EV development module. You can see this appear in the build folder here. So here we have our UF2 file which we can use to program our screen. So if we press the boot select button on the Raspberry Pi Pico on the development board, this will open the folder which represents the memory of the device, and then we can click and drag the UF2 file onto the device, and this will program the Raspberry Pi Pico with the code we have just generated. And here you can see that the code is now running on the Raspberry Pi Pico, but this is just a static display list with no touch functionality. So I've generated some touch functionality previously, and we're going to paste this into the project now. So if we copy this display list, which includes some functionality to interpret touch inputs and color the rectangular output, and rebuild the project, this again will generate the a new UF2 file, which we can then use to program the MM2040. So similar to before, boot select opens up the memory device associated to the Pico, drag the UF2 file on, and we've programmed the device. Now you can see that the light library that is EVE MCU Dev is running the full application along with the touch input to color the output rectangle from our color wheel. So the final one I'm going to discuss is EVE Asset Builder. This is a toolchain which can be used to convert any assets required in your application to EVE readable formats. It also allows us to generate flash images for EVE devices which contain onboard flash interfaces, as well as custom touch generation for touch controller support that isn't natively supported by EVE devices. So we can create, this is the EVE Asset Builder toolchain, and we can create a session which relates to the project we're working on. First utility here is an image utility, which we can use to take input image files and convert these into a number of formats, such as ASTC or ARGB1555. Selecting convert will convert the image and produce an output format file. We also have a PNG and JPEG validator. This validates that input PNG or JPEG files can be used directly with our command load image command, one of the lower level EVE commands. And this allows you to load images without having to convert them. We have a JPEG optimizer as well, which can optimize JPEGs for size or quality. If you want to store these on, for example, program memory on your MCU or flash on your MCU, you can change their size. Next, we have a video converter. This allows us to convert MP4 and AVI files into an EVE readable format, which can then be played back on the screen via the command play video command. Next, we have an audio converter, which allows us to convert MP3 files into audio files, which can be played back on EVE via the audio interface, via simple commands. We have a font conversion utility, which can take input font files, such as TTF or OTF files, and then convert these into EVE readable formats, so you can have custom fonts. This also allows us to support multiple languages, such as Chinese or Japanese characters, presuming the input font file also supports these. So then we can create a conversion, which includes these characters, and print them out on the screen. For example, it also gives us some bitmap formats that we can choose, such as ASTC or L8 to L1, and these just gives us different sizes. Next, we have an animation converter, which allows us to take GIF images and convert these and play them back as animations on EVE panels. And this is good for splash screens. We have our flash generation utility here. And this allows us to add graphics assets, such as custom fonts or images. For example, we'll add an image here into a binary image, which we can generate and then program to attach flash devices for the BT81X or BT820. You can use a USB to SPI or Raspberry Pi Pico to interface to EVE with this utility. For example, here we're using the 4222 to detect flash via the EVE chip. We can then program or read back the attached flash as required. We have a flash diagnostic tool. And then moving on, we have the disassembler. This is useful for taking raw SPI captures of the bytes issued to EVE over SPI and converting these into a human-readable format. This is useful for debugging your SPI captures to ensure you're sending the right commands to EVE. Next, we have our custom touch firmware generation utility. This allows us to compile custom touch firmware patches, which will allow support for touch controllers which are not natively supported by EVE, therefore expanding the amount of LCD screens that can be used with EVE. We have an asset compressor, which can take assets and compress them, and then these assets can then be inflated into EVE's graphics memory using the command inflate option. This is useful if you're not storing assets on the attached flash, and perhaps you're storing them on the MCU's flash. Similarly, we have a validator and decompressor tool in here to ensure that these can be valid or decompressed. Finally, we have a binary to C conversion utility. This is useful for taking, for example, output conversions from images and placing these into C arrays, which can then be pasted into your source code. For example, let's convert the image here, the raw image output that we have, and this will create a C file, which we can open in our preferred IDE or text editor. And as you can see here, it's generated the data into a large array. Okay, I'm going to pass it back to Graham now, who's going to cover the final code examples along with our code libraries, LVGL and AI.
Thank you, Aaron. Yep, so Aaron's covered some of the graphical design tools that we have that allow drag and drop development of your UI. We also have a range of codes, libraries and examples which include the EVE apps and EVE MCU dev libraries, which you can use to develop with EVE code directly in your application. With EVE's object-oriented commands, developing and maintaining a code-based application is easy, and it allows you to integrate it rapidly with existing applications. We have our Programmer's Guide available here from the Documents page of brtchip.com, which details all of the commands, for example, the set bitmap command shown here. Libraries provided by Bridgetek handle the work of translating these to SPI transfers, allowing you to focus on creating your UI in the high-end application. It's also easy to port your code to a different MCU. You can download our EVE Apps library from this GitHub repository, and we have an overview on the same page of the contents of the library. Up at the top, we have the library files themselves under the common directory. And we also have a range of demo apps, which are full demonstrations, and also a sample app, which demonstrates a wide range of EVE techniques and features. And if you'd like to download the EVE apps code, you can download from this menu here. As one example, we're going to show you the gradient demo here, which comes with that library. This demo has projects for Visual Studio via USB to SPI, Visual Studio Emulator, and for the Bridgetek FT99XX MCU. If we open the emulator project, this allows us to develop and test our code without any EVE device connected. We can run the project as shown here, and the window then appears with an emulated EVE screen and no hardware required. We can use the EVE gradient widget here with 2 touch controlled points defining the beginning and end, and then we also have a couple of EVE sliders which allow us to change the colour as well. We also have the EVE MCU Dev library, which is a portable library which currently supports more than 12 different MCUs and platforms to host EVE. For example, you can develop your user interface and run on a display via Visual Studio with a USB to SPI adapter, and then build the same application for your RP2040 MCU. The layered model also makes it easy to add other MCUs. This GitHub page includes documentation to make importing to your own project easy. Here we use the USB to SPI FT4222 build of the code via Visual Studio. We can open the solution here, and we can see the main EVE example.c file, which is this part shown as the touch handling. Once we run the code, we can see EVE's built-in calibration screen coming up. And once we've done that, we can see a square colour picker, and we can interact by moving each of the 2 points individually. We can also use the multi-touch features of the BT817 to move both together, and indeed we can move up to 5 points together. So now we've developed the application, we can now easily import that code to any of the MCUs available in the library, or indeed to any other MCU that you prefer. The next platform we're going to talk about is LVGL, and how you can run your LVGL project on EVE. In this example, we're going to show you how to download the Bridgetek EVE Apps library and how to combine this with the LVGL project. We're then going to show you a simulation via the emulator on Visual Studio, and we're going to deploy it to an RP2040. So this is the download for the example from our GitHub page. And on the page, we can follow these steps to download and build the example. You can see we have the example itself, and which is the LVGL widgets demo. And then we also have our Bridgetek EVE Apps, which acts as a library layer between LVGL and EVE. On the same page, we have some instructions here to build the code for the Raspberry Pi Pico platform, and also some instructions on how to build it for the emulator platform. And I'm going to show you both of these in a few seconds. So in the command window here, we've completed the instructions that were shown on the page. So we've downloaded both of those code files and we've merged them together. And we can now see the demo LVGL and the EVE Apps folders on our own computer now that we've downloaded them. We can preview the demo now using the EVE Apps emulator, which is available here. If we go to the demo LVGL folder in the MSVC emulator, we can open up the project solution file here. We can first of all check the correct platform settings, in this case BT817, and the emulator and the WVGA display. And we can now run it, and on our computer monitor, we have an emulated version of our LVGL project. And as you can see, it easily allows us to add features such as multiple tabs to select pages, as well as scrolling up and down on the page as shown here. We can add scroll bars and toggle switches. We can even configure color themes using this menu here. And we can implement scrollable charts where we can hover and click to view the data point values, and also an equivalent chart as a bar graph style. Can also add other common controls such as checkboxes, and also controls such as scrollable list boxes as shown here. So now we've emulated the code on the computer monitor, we want to go and build that for a microcontroller. So we can go back to the developer command prompt and we can follow the instructions shown. So in the developer command prompt, we're following these instructions, and first we use the CMake, and we've added the details BT817, WVGA display, and RP2040 as our platform. And we then run the nmake command as shown in the instructions, and this produces our UF2 file, which we can load into a Raspberry Pi. So as Aaron did before, we hold the boot button on the MM2040 EV, and this boots the Raspberry Pi to produce a storage device, and we can simply drag the UF2 file in, and our application will begin to run shortly. And as you can see, we now have the RP2040, and it's now running completely independently of the computer, and we have the same application which we've emulated just a few minutes ago using the emulator project. So you can now continue to take this project and build it into your final application. The final platform we're going to talk about today is how you can use AI to help you create EVE widgets and other components for your design. In this example, we're going to show you how to prepare a framework project, in this case with a FT4222 USB to SPI. We're going to show you some details and code examples that you can provide into the AI prompt, and we're going to ask AI to generate our code for a color picker, and then to further optimize and add a couple of features. And finally, we're going to take that code, paste it back into the framework, and then run it on the real hardware. This is the Microsoft Copilot platform, and when using AI to create EVE widgets, it's important to create a specific and detailed prompt to get the best results. Here we've indicated to the AI engine that it should behave like a software engineer when generating the response. As well as describing the application as a color picker, we give key details such as the EVE device, Bridgetek BT817, the module itself, ME817, the screen resolution, the software platform Visual Studio 22, and the USB to SPI connection. We also describe the color wheel and the indication box. Since this is a type of custom widget that normally requires an image, we specify that the image should be created by the code and then loaded into RAMG. We could instead create an image ourselves as a PNG or RAW format and then ask AI to load it. We also specify that capacitive touch should be used. Since there are multiple EVE libraries online, telling the AI engine specifically which library to use and providing examples helps avoid it generating code using a mixture of different libraries. In this case, we want our new application to drop into an existing framework, although it could also generate a full set of project files. One other suggestion is to provide it with a small framework project, such as our EVE Apps or EVE MCU Dev. Here's a small example which I built for our FT4222 USB to SPI interface. The demo generates a small UI with a gauge and a numerical readout, and once the calibration completes, you can see the gauge itself and the touch buttons to increment and decrement the gauge. And based on this project, which is already running, we can actually add this into the AI engine. As you can see here in the prompt, we've added some of the key files to give it a reference to use. And here we can see the AI as the process of generating the code. We get a summary of its understanding, we get the layout of the application, we get details of the bitmap that we've asked it to create and how it's going to implement touch. And finally, here's the code that it's generated. It also asks if we want enhancements, such as to make it more modular for use in your application. In this case, I asked it to add a heading for BT817 color picker, and it's described the additional command text that we require. So we can now take this code and actually paste it in to replace the earlier application that we had. So as we can see, the code is generated. We have a color transfer function here, along with a generation of the color wheel. It actually generates an image in RAMG and calculates the color wheel itself. And we then also have a function which is generated to read the touch XY and check which color is at that location in RAMG. And then we have the main loop which we asked it to generate. So you can see in the main loop here, we call the function to generate the color wheel just once at the beginning. And then each time round the loop, we process the touch and we then render all of the on-screen items, including the text command at the bottom there that we asked it to add. You'll notice a couple of commented items. It did make a couple of minor syntax errors from a different library, so I've corrected those here, but in general, if you highlight that to the AI engine, it will actually correct them based on the files that we've provided. And now we can basically click run, and we can just run this application over USB to SPI, and there's our color picker, which the AI has generated. It includes the heading that we've asked for, it includes a cursor to show us the selected color, and also the rectangle, which is showing us the color that the user has chosen. So now we have that code, and we have it in a format that works with EVE MCU Dev library. We can then easily paste that code into any of the supported MCUs, or indeed, if you want to add another MCU platform, we can use it with that as well. So overall, we've shown you the flow where you can, when you're developing an EVE application, where you can design the user interface using one of our toolchains or code-based methods. You can compile and simulate the code and then make changes to refine it. And finally, you can deploy to the hardware. And so we've given you an insight, a brief insight into 6 of the different tools and approaches, ranging from drag and drop approaches to code-based approaches. With these tools, developing stunning and interactive UIs is easy with EVE. We've got here the QR codes for the tools and the examples that we discussed during today's webinar. So you can scan these codes here, download the tools, and begin developing your application and experimenting. We'd also like to hear from you on any innovative ideas that you have for projects that would use EVE. And for the chance to win a 15.6-inch display with our BT820 board device on board. To enter the challenge, you can submit your details along with an overview of your project as shown here, and also some of the technical details about how you would implement it. So please scan the QR code to get started in submitting your entry, and wish you good luck. We'd also like to hear what you think of our products and services via our product customer survey. So we have the QR code here if you'd like to scan that to begin the survey, and for a chance to win a Galaxy Watch 7. So it's now time for the Q&A session, so I'm going to hand you back to Gavin, who's going to take your questions from me.
Thank you, Graham. Thank you, Aaron. Yep, it's now time for the Q&A. If you've got any questions, please submit them in the Q&A chat box at the top of your screen. While we're waiting some questions, I'd like to let you know about the next webinar, which will be the 3rd in the series, and the title is Powering Performance, the Hardware Behind EVE. It'll be the same time as today, and it's on the 24th of June. Okay, so I'll get the ball rolling with a question. So the color picker, where could you see that in a real-time application?
So our color pickers are used in a wide range of applications. One particular application is in smart lighting control, where the color picker allows users to easily pick any color in a very intuitive interface. They're also used in things like allowing your users to customize the user interface. In the earlier LVGL example, we showed a case where you can change the color scheme used in the interface. And so a color picker is another way to do that, so users can pick their preferred color.
Thank you. Okay, thank you, Julian, for your question. Are there tools available on Mac OS, and how much do they cost?
So our toolchains are free. All of our examples and libraries are free to access on our GitHub. Our ESD, ESE, and EAB toolchains are free. Unfortunately, these are not supported on macOS as of this time, but the lower level libraries, such as MCU Dev, can be ran on macOS as long as you have the correct compilers, etc., for the MCU you require. So yes, unfortunately, as of this moment, the toolchains are not available on macOS, but they are free to use.
Thank you, Aaron. Any more questions from the audience? Okay, so during the show you had a module. What is that display? Can you give us more details?
We were using the DP0701-01A module, and this is a TFT display module that we currently sell, and you can purchase to put into your application if you so desire. This is a 800 by 480 WVGA resolution TFT display module. It has a capacitive touch controller which supports up to 5-point multi-touch and utilizes a 50-pin RGB FPC cable to drive the display.
Okay, thank you. Anybody else? Any other questions? So my last point I'd like to add, if there's no more questions at this time, maybe you may think of some after, just send us an email and we'll get right back to you. And as mentioned at the beginning, this has been recorded, so you'll be able to rewatch the whole webinar and share it with your colleagues and customers.
Julian's asking another question. He says, the end result of compiling is SPI commands for the MCU to send to the Bridgetek chip, correct? The display program runs itself on the MCU. Yes, so the EVE series of graphics controllers, they take commands over the SPI interface, which you can find in the programmer's guide, the lower level commands. And essentially you are correct. You would compile an application which issues screens to the device over SPI. And these screens are contained in a stream of SPI bytes that you would send to EVE. EVE then generates the screen content based on these commands. So the idea is that it offloads the computational effort required to generate screen content from your MCU. One of the nice things about EVE is that if you have a screen that does not need updated frequently or for every refresh cycle of your panel per se, you don't need to continue to issue these SPI commands to EVE. So for example, if you have the color picker screen, nobody's touching it, you don't need to update the screen, you can send one list of SPI commands via your microcontroller to the EVE chip, and then EVE will continue to render this version of the screen continuously until you need to update the display with, for example, touch inputs, or a clock might change on the display, or something like that. And then you can get your MCU to reissue a new set of SPI transactions to the EVE chip, which will then update the contents on the screen.
Thank you, Aaron. I hope that answers your question. We now have a new one from Miroslav. When will the BT822 be available?
The BT822, we currently offer the BT820, which is a version with external RAM. We would need to check with our commercial team on the future products, but we'll certainly do that and email you back. Thanks.
Thank you, Graham. Julian's got another question. Is there a way to estimate the computational load of the display program? Is it possible to ask it to do too much too quickly?
In general, the device itself generally involves loading a list of commands in, and it can support quite high rates, but we have a set of pointers which tell you how full the FIFO is, and so you can send commands in until the FIFO is full and until they're processed. So we have a method of flow control that helps to ensure that you don't send the data too quickly and lose any. But because much of the processing is done on EVE, many of the actual processes such as scaling, rotating images, or many of the dynamic things can actually be handled by EVE themselves. And because the command set is very compact, it actually requires very little bandwidth to send.
Thank you, Graham. Okay, that's been some good questions. Any more?
Oh, there's one in the chat.
Yeah, I can see it. Where can we download the video of the webinar and any of the other webinars in the series?
So, yeah, we've got those on our YouTube channel, and we'll actually be emailing out a copy of the video after the webinar. So you can also, we'll include a link to the first part in the series where we went over the basics of what is EVE and some of the key features of EVE. So we'll send out links to that and also the recording of this webinar in an email shortly.
Thank you, Graham. Anybody got anyone? Oh, Julian, thank you guys. You're very welcome. Glad you could join. Okay, last chance for a last question. Anybody got any others?
Oh, here's one from Alex. With the LVGL implementation, are there any widgets that are not supported?
I believe there may be a couple, such as dotted lines. We would need to double check that our implementation for LVGL is still an ongoing project, but we can certainly get back to you with a more definitive list of the few things that may not be supported currently. But we'll check with our dev team and we'll certainly get back to you by email after the webinar. Thanks.
Thank you, Graham. Thanks for your question, Alex. Any others? Okay, that's been good. Some good questions. Thank you very much for your feedback. And we will now conclude the webinar now. Thank you for your attendance.
Yeah, thank you very much.
Thank you.
Thanks, bye.
Bye for now.